Okay, good afternoon, everyone. And for those who just joined, and we are just to start the second seminar of the day. And now it gives me very pleasure and honor to introduce the second speaker of the day, Professor Huang Haitao from Department of Applied Physics in Hong Kong Polytechnic University. So the title of his talk is Ferroelectric Materials for Energy Applications. So let me briefly introduce Prof. Huang Haitao. So Prof. Huang obtained his bachelor degree from Shanghai Jiao Tong University and the master degree from Shanghai Institute of Metallurgy and a PhD degree from Nanyang Technology University in Singapore. He is currently the professor in the Department of Applied Physics in Hong Kong Polytechnic University. His research interests include material for energy storage and conversion technology. He has published over 280 papers in many top journals, that including Nature, Nature Electronics, and many more. So among many prestigious academic awards, he has won the Science and Technology Award second class from Minister of Land and Resources of China in 2017, and the Natural Science Award second class from the Minister of Education of China in 2019. He is currently the Associate Editor of Advanced Material and Devices, and the editorial board members of several SAI journals. According to recent Stanford citation ranking, he is listed among the world's top 2% scientists. Now, without further ado, let's welcome Professor Huang to give us his wonderful talk.
Thank you, Professor He, for your nice introduction. Let me share the
You may share a screen now.
Okay. So can you see my PowerPoint?
Yes, it all works. You may start.
Okay. Today my topic is on ferroelectric materials for energy applications. And here is the brief outline for today's talk. First, I'll give a brief introduction on ferroelectrics. Then I will introduce what we have done in the past few years, mainly in three different topics: the ferroelectrics for energy storage and solid state cooling and catalysis. And finally, I will give a conclusion. So first, let me give a brief introduction on ferroelectrics. The ferroelectrics is a material that have a spontaneous polarization, and that spontaneous polarization can be reoriented by applied external field. And the ferroelectric material normally have a non-central symmetry structure. And actually, nowadays, we have four main groups for the central symmetry structure, which is perovskite, tungsten bronze, pyroelectric, and bismuth titanate layered structure. Today, I will mainly focus on the perovskite structure, which have a chemical formula of AbO3. And here, A atom is located on the corner of a unit cell, and B is at the center of the cubic unit cell, and oxygen is the phase center, six phase centers. So normally for the perovskite structure at a high temperature, it carries a cubic structure, and the positive ions and negative ions have their centers located at the same position. So at a high temperature, there's no spontaneous polarization. However, when the temperature is low down, below the Curie temperature, there is off-center displacement between the positive ion and negative ions. So a net spontaneous polarization is being generated. And we can use the Landau phenomenological theory to explain these phenomena. At a high temperature above the Curie temperature, the potential energy as a function of polarization shows a parabolic curve. So the minimum energy corresponding to the zero polarization when the positive ion and negative ions are located at the same position. Now, when the temperature is low below the Curie temperature, and the potential well becomes a double well. So now you can see the for the minimum energy, the corresponding polarization should be non-zero. Okay, so there is a relative shift of the positive ion and the negative ions. Then when the external electric field is being applied, then the two double wells will have unequal potential energy, right? So when the electric field is applied along a negative directions, and for the negative polarization, it has a lower Gibbs free energy. So all the material will have polarization aligned along the negative direction. And when the electric field is being switched to the positive directions, then the polarization will also be switched to the positive direction. So if we measure the polarization as a function of electric field, normally for ferroelectric material, we get this type of hysteresis loop. When the electric field is being removed, the polarization will normally not go back to zero. The reason is that all the is due to the clamping of the domains, because there are a lot of domains existing in the material. So when even when the electric field is being removed, the clamping of the domain will prohibit the complete randomization of the polarization. So there is a net spontaneous polarization. And the spontaneous polarization of ferroelectric material actually is not a constant. It is responsive to many factors. For example, you can apply a mechanical stress or strain, right, to change the polarization. You can also change the temperature to get a different polarization. And the polarization may even be affected by a magnetic field. The philoelectric material actually belongs to a group of the pyroelectric material. Here, pyroelectric means when you change the temperature of the material, the polarization will be changed. And it also belongs to a even larger group of the piezoelectric material. Piezoelectric material is a kind of material when you apply a stress or strain, you generate a charge on both surfaces of the material. And all the philoelectric, pyroelectric, and the piezoelectric material belongs to an even larger group of the materials, that is the dielectric material. Dielectric material means when you apply electric field, there will be a polarization and with respect to the applied field. So for different types of materials, you can find there are different applications for energy. For example, the dielectric materials can be applied in the parallel plate capacitor. Piezoelectric material can be used to harvest the mechanical energy, and the pyroelectric material can be used to harvest the thermal energy, such as it can act as a device for cooling, solid state cooling. So now in the next few slides, we'll talk about the first application for the philoelectric material to be used for electrical energy storage. And the device we use is mainly parallel plate capacitor. And in comparison with the electrochemical supercapacitor, you can see for the parallel plate capacitor, all the charge are actually being stored at the interface between the electrode and the dielectric material. While for the electrochemical supercapacitor, those charge can be stored at the surface of the active electric material. So since the electrochemical supercapacitor has a much larger surface area than the interface between the electrode and dielectric in the parallel plate capacitor, so electrochemical supercapacitor has a larger capacity or a higher energy density. So if you look at this diagram plot, you can see for those pseudocapacitors or double layer capacitor, all of them belong to the electrochemical supercapacitor. It has a higher energy density than the conventional double layer capacitor. But due to the easy charge transfer, right, the conventional parallel plate capacitor can be charged or discharged very quickly. So it has a much higher energy power density as compared to the electrochemical one. And if we use ferroelectric material, as we just mentioned, right, when you apply electric field, there will be a hysteresis loop being developed. So when you discharge, when you reduce the electric field, you can see the polarization does not go back to zero when all the electric field are removed. The released work due to the removal of the charge can be calculated by the integration of this shaded area. You can do this type of integration. So the energy release actually is the moving of charge on the external applied field. And from this figure, you can see due to the existence of the remnant polarization here, and the energy release may not be very large. So if we, instead of the ferroelectrics, if we use anti-ferroelectrics, anti-ferroelectrics has a feature that when you remove the electric field, right, the polarization becomes zero. So you can greatly enhance the released charge and also the released energy. So by using anti-ferroelectrics, you can improve the energy density. And another thing is, if you look at the hysteresis loop, you see for a capacitor, you need to charge the capacitor before use, right? So when you do the charging, right, the energy required should be integrated along this charging curve, right? When it is removed, it will be discharged from the above curve. So there is a difference between charging and the discharging. The difference in energy corresponding to this white area, and this corresponding to the energy loss during the charge and discharge. And for practical application, we wish this type of loss to be as small as possible. So ideally, we need to have a very slim hysteresis loop. And this slim hysteresis loop can be achieved in a relaxer type of the ferroelectric or anti-ferroelectric material. So now based on this very simple discussion here, so ideally, if you want to make use of ferroelectric materials for parallel plate capacitor application, yeah, we wish to have a coexistence of different phases. So our first example is we make use of a lead-free perovskite material, which is a solid solution between this BNT. BNT is this bismuth sodium titanate, and BT is the barium titanate. It forms a solid solution, and this is the phase diagram for the BNT BT. You can see the different, according to the different composition, right? The material, the solid solution can have different phases, such as the ferroelectric phase, when this barium titanate has only a very small amount, and it can also have anti-ferroelectric phases when the barium titanate composition is ranging from 6 to 10%. So as we just discussed, the composition we chosen is very close to the phase boundary between this ferroelectric and the relaxer anti-ferroelectric phase boundary. And in addition to this coexistence of the two phases, we also add some other elements to modify the composition. We add the lanthanum on the A side of the perovskite. The purpose of this is to disturb the long-range ordering of the polarization state. And we also add a small amount of zirconia on the B side cations. And the purpose of this is to tune the Curie temperature. We want to change the Curie temperature to bring down the Curie temperature. Okay, so finally, the composition we have chosen is this one. Then in order to identify the different phases, we can use electron beam diffraction. And here is some methodology, right, to identify the two different phases. For ferroelectric phase, we can observe some superlattice reflection. You can see here we have a superlattice reflection, and the index is odd. You have 3 odd numbers. So for ferroelectric phase, we can observe this superlattice at the 3 odd refraction index. And for the anti-Philoelectric phase, we can observe some superlattice spot at this index of 2 odd number and 1 even index. So this is a feature for the anti-Philoelectric phase. So based on this kind of knowledge, right, we can do a detailed microstructure catalyzation, and we do find the 2 type of superlattice fringes exist, and you can see we found all the odd index superlattice, and we can also find this superlattice for the 2 odd and 1 even index, and this corresponding to anti-Philoelectrics, this corresponding to the Philoelectric phase. So from TM, we observed the coexistence of the FE and the AFE phases. And also we found some streaks along this direction, and this is a feature of the so-called incommensurate modulation, and it reflects the relaxer property of the material. So this material also contains a relaxer phase, which is the so-called polar nano region. And from the analysis of the dielectric spectral, we can also provide additional evidence. For example, this is the dielectric constant function of temperature. We can use this Lorentz fit to fit this dielectric spectrum, and from the fitting, we can find this delta A is larger for the thin film sample as compared to the bulk sample. So this means in our thin film sample, we have more relaxer dispersion. And we also measure the dielectric constant as a function of the electric field, external electric field. And the obtained result can also be simulated by this formula. And the first term in this formula means the lattice phono contribution. And the second one, which is indicated by this red curve, right, is caused by the polar nano cluster. And we can, from the simulation, we can find this dielectric constant has a larger component of this contribution from the polar nano cluster. So this is another evidence that the film consists of a lot of polar nano regions, which is a feature of the relaxer Philoelectrics and anti-Philoelectrics. Then we measure the P hysteresis loop. So on the for different orientation of the film, you can see that we obtain a very high energy density. And if we can further enhance the applied electric field up to 3,500 kilowatt per centimeters, and we can see the obtained energy density can be even larger. And also the efficiency is also very high, above 95%. This high breakdown voltage of the film is due to the very good epitaxial film quality. Then we also examine the cross-section of the film on the substrate. Okay, we use this lanthanum strontium magnet as the bottom electrodes, and we deposit our Philoelectric film, and we can find there is a very nice epitaxial relation between the film and the substrate. When we do the electron beam diffraction, we found no splitting of the spot. That means the substrate and the film are having a very good epitaxial relation. And we also analyzed the leakage current as a function of the applied field, and we found that the leakage current is controlled by the so-called Buck limited conduction mechanism. And finally, we plot the energy density of our film in the Regen plot. And by comparing with other lead-based material and polymeric material PVDF, we found our energy density is very high. Even up to this work was published a few years ago, and even up to now, this is still the record for thin film materials. And we ascribe this high energy density to the coexistence of different phases, and also the very good film quality, which endow the film with a high breakdown field, so we can apply a very large electric field without break down the film. And also due to the film consists of a large amount of relaxer components, so the efficiency of the device, the charging and efficiency is also very high. And we further extend our work to other type of thin film, to for example, to this 111 oriented lead barium zirconium film, and also achieve a good result. The time limitation, I'll not go to the details. So now let's move to the second part, the electrocharic cooling. And this figure compares the electrocharic cooling to that of a conventional compressor. And let's look at the conventional one first. In the conventional case, when you do the work against the this cooling device, right, you compress the liquid or gas, right, inside this cylinder, so it will increase the temperature. Then you release the heat to the surroundings, bring down the temperature. Then in the next step, there is a adiabatic expansion. So during this expansion, the temperature of the material inside is cooled down. And when you put this material in contact with the surrounding, it can take the heat from the surrounding. So this is the one complete cycling. So when you apply the do the work, right, to the engine, it can actually remove heat from one surrounding to one media to another one. So this can work as a cooling engine. And similarly, for this electrocharic cooling device, when we initially the material has a spontaneous polarization that are randomly oriented. When you apply electric field, you align all the polarization along a similar direction, and this will result increase in the temperature. Then you release the heat to the surrounding to bring down the temperature, and after that you remove the electric field, and under this adiabatic process, the temperature of the material will be lower down, and then you can move this material to in contact with the surrounding and can take off the heat. So this is the one cycling for the electrocharic refrigerator. And if you reverse the cycle, actually you can make it as a the heat engine. For example, this figure shows two P hysteresis loop. Right, one, the black one is obtained at a low temperature, and another hysteresis loop, which has a smaller polarization, is obtained at a higher temperature. So if you cycle this material, right, along these four passes, then you can see when you go from 1 to 2 to 3 and 4. So during this charging state, right, actually you input work to the material, right? During the discharge state, you release the energy. Okay, so through this cycling, and you let this material to work between two different heat sources, right? You can make it as a heating to turn the thermal energy into use for work. So this is called a so-called pyroelectric ocean cycles. And for the electrocharic cooling, we can use this Maxwell relation to calculate what is the temperature change when you apply the electric field or remove the electric field, and also the corresponding change in the enthalpy. Okay, so let's talk about our materials selection first. Similar to the parallel plate capacitor case, right? Here we also choose a material with the coexistence of different phases. So let's look at this material. This is the lead tantalum material, and with the B side to be replaced by tin and zirconia. So these three elements will form a phase diagram here, and we choose the material composition near these two anti-Philoelectric phase boundary. One has a tetragonal phase, the other has an orthorhombic phase. Then we also add some doping, similar to the previous work. We add some lanthanum doping, right, to disturb the so-called long-range ordering, to introduce some relaxer behavior into the thin film. So finally, the composition of the material is this one. Then we deposited this material on different bottom electrodes, such as platinum and lanthanum nickelate, and a combination of lanthanum platinum as the bottom electrode. And we also adopt two different type of the annealing process. This thin film is processed by the soldier processing, multiple layer deposition. So in the A-type processing, we actually deposit the film layer by layer. Okay, then after deposition of each layer, we do the annealing. Okay, in the B-side deposition strategy is we deposit all the layer. Okay, then do the final annealing. So we use two different types, and later we do some detailed microstructure catalyzation, and we do find some superlattice refractions, and with diffuse streak, which also indicate the polar structure. And we found this lanthanum doping can strengthen the interaction between the anti-Philoelectric and the Philoelectric coupling. Then we measure the hysteresis loop at a different temperature, and based on the this hysteresis loop, we can calculate what is the temperature change due to the removing of the electric field, and we found the corresponding temperature change is positive. It is also very large, around 200 degree. And when we applied this thin film for the ozone cycles, we cycle the material between 20 and 260 degrees. We measure the two different hysteresis loop. One is the black one at the low temperature, another is the blue one, the higher temperature. Then we can see if we build the ozone cycle as indicated by this red arrow, right? We can actually get a work output which is equivalent to the area of this shaded part. The maximum achievable output of the work, right, is around 6.10 joule per cubic centimeter. And if you compare this result to those thermoelectric material which work between the similar temperature range, you can see actually the energy release, right, can be is much higher than those thermoelectric materials. And similarly, we also did another work by choosing this type of material, BCT, BMT thin film, and we fabricate this film with 111 preferred orientation. And this material was characterized to have a Philoelectric phases and with relaxer behavior. And the feature of this material is when we apply electric field, we found a phase transition from the initial tetragonal and orthorhombic phase to the finally to the rhombohedral one. And we also observe a very large negative electric current effect. And normally we know when you apply, when you increase the temperature of this material, right, the polarization will decrease. So the electric current effect will be normally positive. So why here we get a negative electric current effect? Then we use a phenomenological theory to try to explain the result. We found it is due to the phase-induced, is due to the field-induced phase transition. Initially, You see, the orientation of the film is this 111 direction. Initially, our film is around this tetragonal direction, which is 001, or we have also have rhombohedral phase, orthonormic phase, which the polarization is along this 110 direction. Both directions are different from the 111 direction. So the measured polarization is just a projection of this two polarization around the 111 direction. And when we apply an electric field, right, the phase is gradually transferred to the rhombohedral one. So finally, all the polarization is switched to this 111 direction. So although when the temperature is increased, although the polarization value is decreased, but now all the polarization are along this film normal direction. So actually the measured polarization is still increased. So that's why we get a negative electric effect. Okay, now let's move to the third part, the Philoelectric catalysis to generate hydrogen. First, some just brief introduction on the hydrogen generation. And in the industry, people use this steam reforming, right, to form to get this hydrogen in a large scale. And the hydrogen can also be produced by electrocatalysis. Electrolysis, right? When you apply a voltage above over the theoretic voltage of 1.3, you can actually split the water into hydrogen and oxygen. And this is the Purbeck's diagram telling you the potential required for the hydrogen release and the oxygen release. And people can also use sustainable approach to get this hydrogen. For example, they use photocatalysis. And when the photon is shy on a photocatalysis, it excites one electron from the valence band to the conduction band. If the conduction band is more negative to the hydrogen evolution, so it can generate hydrogen. And of course, if the hole left in the valence band has a right position, then it can also create hydrogen by using this photocatalysis. And sometimes, if the conduction band of one material is not enough to generate the hydrogen, and if the valence band of the another material is not suitable for the oxygen production, people can use a so-called Z-scheme strategy, right, to add a redox mediator, right, to combine these two materials together, and it can effectively transfer the electron from the conduction band of this material to the hole of the valence band of another one. So finally, it can realize efficient water splitting by making use of the electron from the conduction band of this material and hole left on the other one. This is the this scheme strategy for the overall water splitting. Now let's introduce our method. We can also use phyloelectrics for the water splitting or the hydrogen generation. Remember, for phyloelectric material, right, the spontaneous polarization is responsive to the heat or the applied stress. So when you change the temperature, you will get a pyroelectric voltage. And similarly, if you apply a stress, right, you will also get a voltage. And if you vary the temperature change, if you cycle the temperature change or cycle the applied strength or strain, then the surface of the phyloelectric material will have surplus charge being released under the external cycling of the temperature or the applied stress. And this released charge will participate in the oxygen evolution or the hydrogen evolution if the conduction band age or the valence band age are suitable for the water splitting. So this mechanism is quite similar to the photocatalysis. But if you compare the photocatalysis, then we'll find a problem. And this is the early design for making use of the Philoelectric material for the water hydrolysis. You can see when the temperature of the material is being changed, it generates a pyroelectric voltage. And if the voltage is large enough, it can split the water. But if we calculate the current release due to the pyroelectric effects and compare to that of the photocatalyst, actually, we found the current release by the pyroelectric effect actually is 2 or 3 orders of magnitude lower than of the currently available photocatalyst. So in order to make this pyrocatalysis more efficiently, we have to we cannot adopt this external design. We have to put the material into the water, and we have to make use of small particles, nanoparticles. The purpose of nanoparticles is compared to the bulk material, we have a much larger surface area, and for the pyroelectric material and the piezoelectric material, the charge is only generally on the surface. So the surface area is very important for the enhancement of the photocatalysis, for the enhancement of phylocatalysis. So this is the first example we we fabricate these barium strontium titanium nanoparticles. Then we characterize its ferroelectric properties, and we also measure the pyroelectric current released when we cycle the temperature. When there is a cyclic temperature change of the material, we can get a pyroelectric current release from the material. Then we do the catalysis. We put these phytoelectric nanoparticles, barium strontium nanoparticles, into the water. Okay. Then after the thermal cycling, we found the release of the hydrogen, and we also compare the two different cases. One case is without the methanol. Okay, in this thermal cycling, there's no methanol being added. Then we found the hydrogen evolution is very small, and when we add methanol, right, we can greatly enhance the hydrogen evolution. The reason for the enhancement is due to the methanol use actually is the whole scavenger. So it can effectively capture the holes generated during the thermal cycling, and to reduce the charge recombination between electron and holes, and therefore we can greatly enhance the hydrogen evolution. And we also characterize its band structure by using spectroscopy method, and we found the band gap of this barium strontium is around 3.08 eV, and the conduction band of the BST actually is more negative than the hydrogen redox potential. So any electrons in the conduction band will be able to participate in the hydrogen evolution reaction. Then we further extend this kind of catalysis, right, to 2D field layered black phosphorin. And we know for the black phosphorin, we do not have any polarization because of the central symmetry. But for the field layer one, the central symmetry is broken. So the field layer black phosphorin shows some phyloelectric property, and then we can we make use of this phyloelectric field layer black phosphorin for the pyrocatalytic hydrogen generation, and we cycle the material in different temperatures, and we found the hydrogen release. And we also found that the black phosphorin can be also used for the biodecomposition, and we found it is really pyroelectric effect, pyroelectric effect, because the change of the decomposition of the die can occur when the temperature is increased from 10 to around 65 degrees, but it keeps almost constant. So when the temperature is hold, does not change, then there's no die decomposition. And when you decrease the temperature from 65 to down to 15, then again we observe the decomposition phenomena, and that is the feature of the pyroelectric material, because the polarization can only change when you change the temperature. If the temperature is constant, there's no change in the polarization, and therefore there's no pyrocatalytic effect. And we also verify the piezocatalytic effect. We fabricate this bismuth ion nanosheet, and to test its piezocatalytic hydrogen generation. And a different situation for this bismuth ferrite is, if we characterize band structure, we found the conduction band of this material is more positive than the hydrogen evolution. So this kind of material will not be able to generate the hydrogen if under normal situation, okay? But when we apply a ultrasonic wave to the material, we do find some hydrogen production. And we also found that the hydrogen production is more significant when the ultrasonic frequency is around 45 kilohertz. And that frequency is very close to the resonance frequency of our nanosheet. We do some detailed calculation to find the resonance frequency of the nanosheet, and we found these two frequencies are really very close. So this also a proof of the piezocatalytic effect. And this material also show a very good stability. So even after a long time catalysis, piezocatalysis, the material still keeps its original morphology, and there's almost no change in the X-ray diffraction pattern. Then the question still remains, why in this case we can get a hydrogen evolved, because the conduction band is more positive than the hydrogen evolution. So we believe that it is due to the piezoelectric voltage generated across the two sides of the nanosheet. So when we add a resonance, right, to the material, when we deform the material, we get a piezoelectric voltage being generated across the nanosheet, and the piezoelectric voltage will tilt the band. It makes the energy band, the band structure tilted, and therefore, we do a detailed calculation. We found the open circuit voltage for this nanosheet is 0.88, and there is a chance for the tilted band edge to be more negative than the hydrogen evolution, and therefore the hydrogen evolution is possible. And we also try the die decomposition of this material, and it is also show effective die decomposition. So finally, let me talk about some future perspective of these three different applications. So for the parallel plate capacitor, there is an increasing trend in making use of the composite material, because this material can withstand a very large electric field. The breakdown field is very high. The only problem is if we want to apply this material, we need to increase the working temperature to be beyond the room temperature. So this is also a very challenge. And also to increase the capacity of the composite, we can do some interface engineering. So we can try to store the more charge at the interface, and therefore the capacity of the material can be increased. And for the electrocaloric cooling, as we just mentioned, right? We have both positive and negative electrochromatic effect. And for efficient device, for efficient cooling device, we wish to have both material. Okay, so nowadays, quite a few, we can only find quite a few material having the negative electrochromatic effect. So there is still quite challenging to find material with a large negative electrochromatic effect. And also, many of the measurement of the temperature change is not direct, is indirect. So we need to find some accurate direct measurement for the temperature change when we apply or removing the electric field. Now, for the catalysis part, phylocatalysis part, if we compare this barium bismuth ferrite to the platinum, so we found although the hydrogen can be more easily absorbed on the surface of the BFO, but when the hydrogen are dissolved to form the hydrogen gas, then it also requires a larger energy. So we measure the polarization curve for the BFOs, and we found if we compare to the commercial platinum, then the property of this BFO is not so good as compared to the commercial one. So the challenging thing is how to find a suitable material with a very appropriate absorption energy in order to enhance the catalysis activity. And we also found when we apply the stress or strain, then under the compression stress, the hydrogen will have the compression stress will lower the absorption energy. Okay, and during the desorption process, we found the tensor stress helps the desorption process. So here the external applied stress, how the external applied stress will affect the hydrogen absorption and desorption process. They need to be fully studied in order to understand the detailed mechanism for the hydrogen generation. And finally, we know for all the provided kind of material, it has a basic unit of the oxygen octahedral. And this is an example for the spinel. Spinel also has oxygen octahedral, and so oxygen octahedral is considered to be the active center for the hydrogen evolution and oxygen evolution. And we have done some work for the spinel structure, and we found by tuning the EG electrons of the oxygen octahedral, we can control the oxygen evolution and reaction activity. So for phylocatalysis, here there's also a lot of work need to be done to fully understand or to find what is the correct descriptor for the phylocatalysis for either the hydrogen evolution and oxygen evolution reaction in order to increase the activity of this material. So finally, sorry, here is the possible application for the different devices. For the parallel plate capacitor, we can apply for the device with very high discharging power. And for the electrochromatic cooling, it can be used for the solid state cooling. For the microelectronics and for the phylocatalysis, it can be used to harvest the waste heat, or it can make use of the oxygen reactive oxygen species generated from the catalysis for the self-cleaning purpose. So finally, this is the conclusion. There's a lot of plenty of room in the philo energy. We can have the synergy between the piezoelectric effect, pyroelectric effect, and also the photoelectric effect. And we can manipulate those synergy on the applied stress strain field or magnetic field or electric field. And there's still a lot of things need to be studied, and this field is emerging and also developing very rapidly. And finally, I'd like to thank all the grants I received, and particularly I'd like to thank my collaborators and all the previous part of the work collaborate with Professor Peng Biaoling, who is a postdoc in my group before and now is in Xidian University. And also I'd like to thank Professor Jiang Yiming from Xi'an University of Post and Telecommunication, which have long collaboration with us. Also, I'd like to thank my current group members. So thank you. And your questions are welcome.
Thank you for Professor Huang for this wonderful talk. It's very informational and inspiring. So while our staff is gathering questions, I will personally ask you one question about your research. So my question is rather general. So what is the general synthetic method for these ferroelectric materials you used in your lab or in general in the field? And because they seem to have quite diverse and complicated structure and composition. So is there any trick in the synthetic method?
Yeah, actually, we use a different method. For the parallel plate capacitor, we use solder method, right, to deposit the film. And we also have used the pulsar laser deposition method to fabricate the high quality thin films. And for the electric current cooling, we also use similar method. It's just a film deposition method, right? Use solder or the pulsar laser deposition. For the last part, for the phylocatalysis part, as I just mentioned, right? If you use bulk material and your surface area is not very large, so it will not be very efficient, right, for the release of the charge. So we have to fabricate nanoparticles. So for the catalysis part, we use hydrothermal method, right, to fabricate high quality nanocrystals. I hope this answers your question.
Yeah, seems a lot of different methods. So it's a rather big field, yes.
Yeah, we have to use different methods.
Yeah, so for different applications. So we do have questions from audience. So first one is, so what kind of instrument and experiment condition do you need for set up such a lab in the field of ferroelectrics?
Actually, yeah, you see, for the fabrication, right, we need the film deposition at the pulsar laser deposition requires a more complicated facility. We have to use a laser, use vacuum chamber, those kind of things. It's also expensive. But for the solder method, it's relatively simple. The only important thing is you have to prepare a very good soil solution. Okay, and that solution should be stable, can last for longer times. And for the deposition of the solder, for the solder deposition is relatively simple. After you have prepared the soil, you have to use spin coater, a very simple spin coater, right, to coat the soil solution onto a substrate. Then you need a hot plate and also a furnace, right, to do the annealing on the thin film. Okay, and the last one for the fabrication of the nanoparticle, it just it's a hydrothermal method you need for the laboratory scale, right? You just buy a very small autoclave, right? You can heat up. You use a oven, right, to heat up the material up to normally 200 Celsius degree. It's normally enough for the hydrothermal synthesis. Okay, so for the material fabrication, the solder and the hydrothermal is very low cost. Okay, but for the pulsar laser deposition is could be quite expensive. Then for the catalyzation part, right, and for ferroelectric material, special equipment need to be used is to characterize the hysteresis loop, the P hysteresis loop. There is some special equipment for this one. For all the other characterization like SEM, TM, and other spectroscopy method, I think it's quite common for any university having a material science department. So normally those are is under the center of the university, right? So you don't have to buy all of these by yourself. Okay, so I think the major investment is just the processing and the characterization of the P hysteresis loop. Is this can be done within 1 million RMB. You can easily set up this kind of lab.
Okay, so thank you for those very specific instructions. I hope that does answer the questions. Okay, so we will have another question about the so what is the main application scenario for ferroelectric material-based energy storage, and how do they compare with other energy storage technologies, especially for capacitors?
For the capacitors, the feature of the parallel plate capacitor is it has a very high discharging power. So as I just listed in the last few slides, right? For the case which requires a very high discharging power, right? Such as the this medical defibrillator device, and also the electrical weapon system, right? You have to use those kind of parallel plate capacitor because the power density required is even higher than the available electrochemical supercapacitors. Okay, and
I see.
And for the electric current cooling, the advantage of this type of cooling, it is a solid state one. Is different from our conventional cooling device, which we use the coolant, right, which is a liquid, right. So you have to compress and expand those coolant, so it generate a lot of vibration. So for this type of cooling, it is a completely solid state one. There's almost no vibration. And for the catalysis part, I don't think in terms of the activity, right? I don't think it's better than any electrocatalyst. Okay, so you can forget about the hydrogen evolution or the water splitting kind of application because it is not efficient. But we can make use of those reactive oxygen species, right? Generally, from the vibration from the surroundings. Okay, so making use of the surrounding vibration, and we can generate some reactive oxygen species, and those kind of material can be used for the self-cleaning. And here is an example shown by Professor Wang Yaojing from Nanjing. They use barium titanate, right, to clean the teeth. You can see there is a comparison between the barium titanate and the one without the barium titanate. So after a long time of vibration, you can see the teeth can be clean. Of course, this process is not very fast, okay, but still it is effective. So especially for those, for example, some building or some places which need self-cleaning, and you can probably apply those kind of technology because it can absorb the surrounding vibration, right, to generate those kind of cleaning species, and it's a long-term cleaning process.
Okay, thank you. I hope that answered the questions. And due to time limit, I think we do have other questions, but let's stop here. And let's thank again for Professor Huang's wonderful talk. And we hope you have a chance to submit to the SmartMath in the future, maybe.
Okay, thank you.
Yeah, thanks again for coming. Okay, so that will we will stop the seminar today now. Thank you for everyone for attending.